A modern hospital ward is in constant, unpredictable motion. Patients arrive, stretchers roll down hallways, and medical staff pivot between emergencies. The physical state of the floor is shifting every minute. But to safely treat patients, administrators cannot rely on estimates. They require absolute, real-time logistical precision. That creates a strict operational challenge. Every physical entity, whether a patient changing rooms, a bed requiring maintenance, or a visitor entering the lobby, has a volatile status. If the tracking system relies on uncoordinated spreadsheets, errors compound rapidly. To solve this, Al Salam Teaching Hospital implemented a proprietary smart bed occupancy management system. It handles these complex admission flows and security checks using a surprisingly lean technical stack: Python, the Flask web framework, and a lightweight SQLite database. This architecture maps complex physical hospital logistics into a series of stable, predictable digital states. To understand the mapping process, we will trace the chronological journey of a single patient, from the moment they enter the hospital to the minute they are discharged, analyzing the specific back-end logic executing at each step. The core concept driving this logic is a state machine. A state machine is a mathematical model of computation where an object can only be in one definitive status or state at a given time, and strict rules govern how it transitions to the next. We will observe this state machine across 3 distinct phases: data modeling the physical ward, operational segregation of staff duties, and automated security at the front doors. By the end, the data will show that effective health informatics relies on forcing physical reality to comply with rigid digital rules. The logistical sequence begins the moment a new patient arrives and requires a physical bed. To record this in the database, the backend utilizes Alchemy ORM. This object relational mapper acts as the bridge, converting Python code into interconnected database tables. First, the ORM establishes the hospital geography, dynamically categorizing physical zones like the ICU, surgery, or pediatrics, so they exist as distinct logical domains. This entity relationship diagram illustrates admission. The software binds a patient record directly to an available bed. To prevent assignment to a dirty bed, the ORM categorizes beds into available, occupied, or maintenance states. Finally, a triage layer assigns priorities: normal, high, or critical, dictating placement urgency. Once priority is matched, the admission transaction is executed with a single click in the interface. This click triggers a database cascade. Assigning the patient to the bed instantly transitions the bed state to occupied. That specific bed is immediately locked out of all future availability queries across the hospital. If medical needs change, the patient transfer protocol activates. The ORM severs the link to the current bed, restoring it to available or maintenance, and relinks the patient to a new bed without deleting any of their previous historical data. When treatment concludes, the discharge process fires. Freeing the bed not only transitions its state back to available, but automatically archives any logs detailing the visitors or companions tied to that specific patient. Alchemy isolates these entities, departments, beds, and people, linking them through strict logic, transforming the fluid hospital floor into a queryable mathematical model. But a data model is only as reliable as the humans inputting the data. Medical staff have highly specialized duties, and the software must reflect that physical hierarchy. This is handled through role-based access control, or RBAC. The system decides exactly who is allowed to view, alter, or delete the database state. This visual funnel maps the tripartite permission structure built with Flask login. Nurses hold exclusive authority to modify bed states. Reception is walled off, confined to managing visitor traffic. Finally, admin bypasses padlocks, maintaining full system access while pulling global analytics. Enforcing these boundaries ensures a receptionist lacks the privileges to accidentally discharge an ICU patient, and an attending nurse is entirely freed from the administrative burden of logging visitor IDs. In this architecture, RBAC enforces the hospital's operational hierarchy at the database level, ensuring that digital data transactions remain strictly aligned with staff responsibilities. We can see this operational enforcement clearest at the hospital entrance. Unmonitored patient companions and visitors present an immediate security risk to the physical ward. To mitigate this, the application logic hard codes a definitive threshold, a maximum limit of 2 simultaneous visitors per patient. If the receptionist attempts to log a third person, the interface evaluates the database query. Once it registers 2 active visitors linked to that specific bed, it entirely locks out the Add Visitor function. Concurrently, a real-time tracking mechanism begins ticking, displaying the exact elapsed time since each visitor cleared the lobby. For individuals staying overnight, the system applies a heavier layer of verification. It records their national ID numbers and phone numbers into a specialized companion log. The system uses the Python DocDocs library to translate digital records into physical artifacts. It pulls vetted records, formats them, and integrates a Python QR code library, stamping an automated, scannable matrix directly onto the document. This creates professional Word documents that can be printed as hard copy ID badges at the reception desk in seconds. When that QR code is scanned upon exit, a precise digital log records the departure time. The system then automatically updates the companion's status from an active presence to an archived historical record. Software logic coordinates the authorization, issuance, and archiving of badges, maintaining a strict audit trail for every person on the floor. While individual nurses and receptionists interact with isolated tasks, hospital administrators require a holistic view of this data. The system provides this via a premium dashboard, utilizing a sleek, glass morphism-inspired user interface to display real-time occupancy statistics. This network diagram details how information reaches the front end. The Reports API continuously pulls data streams, aggregating them into the glowing central interface. Concurrently, the mobile API extends read access directly to handheld devices, allowing guards to verify logs while walking the floor. To prevent stale data from misleading staff, the dashboard employs an auto-refresh cycle. Configurable intervals of 1, 5, or 10 minutes ensure occupancy metrics and stay durations remain perfectly accurate without requiring manual page reloads. Administrators can extract this real-time dashboard data at any time, exporting full patient histories and companion logs directly into CSV files for macro-level review. From defining physical bed limits in a mathematical model to separating staff duties through RBAC logic, right down to generating scannable printed QR codes at the lobby, the Al Salam Smart Bed system demonstrates that managing a highly volatile physical environment does not demand bloated enterprise software. It simply requires aligning the digital architecture strictly with the operational reality of the ward.